Hello everyone, can you hear me? Good. Okay, so give me 1 second. I need to. I'm opening PowerPoint. So I hope you had a great weekend. It was very rainy on Vancouver. It's getting cold. We have a lot of pending stuff for today. Um, okay, good. So we will keep talking about ray tracing realistic effects. We already discussed why this depth of field happen in a real camera, and today we will see how we can actually fake that effect in ray tracing. Right? I mean, I'm saying faking because in the end that is what we usually do. We fake everything. Yeah? Okay, so pending stuff. Well, learning goals for today, we will keep talking about depth of field, which is basically the solution of the depth of field. We will talk about soft shadows, or shadows produced by area lights, right, or area shadows, and also something called motion blur. Maybe some of you already know a little bit about this concept, but we will talk about how we achieve this in our implementation. So pending stuff. The first thing is the shading assignment face-to-face grading sign up. So I think Ibo, you already yeah, you already posted a link for the Google Doc. Yeah, it's there already on the chat. So please, that is super important. Remember, we're almost finishing the semester, right, the term. And yeah, if you have a problem, if eventually you don't appear, or you miss one of your gradings, we will have a problem. So please go and sign up, right? Also, we have the ray tracing assignment. I think a lot of people is already working with that because I've seen questions on Piazza or people that have sent me uh, yes, a couple of emails or things like that. So basically, the labs from from today and the rest of the labs will be focused on the ray tracing assignment. So the TAs will help you to basically to lead you through the ray tracing assignment. And again, I think there are still a couple of things that I probably need to state clear, because we have people that are still asking about like how much of Peter Shirley's code they can use. And I'm already answering Piazza, but maybe you haven't seen it. So you can use Peter Shirley's code. That is perfectly fine. We're encouraging you to actually create your own code, right? I mean, that will be better, and you will learn a lot more. But you can use the code that is provided, right? So you can use that code. It means that, yeah, because many people is asking this because those are basically the first 15 points, 50 points, right? So basically the half of the ray tracing assignment is a code that is already there. Yes and no, because the way we will grade this assignment is also by testing your knowledge about the code, right? But in terms of implementation, yes, you can use the code. That is perfectly fine. Or you can, for example, if you are trying to create your own from scratch, you can also use the same naming conventions, the same variables. You can just literally copying the code from Peter Shirley. That is perfectly fine. It's perfectly okay. Okay. The thing is, in the end, you need to understand the code. So if someone, yeah, if you don't have the time, right, to write the entire code for the first half, because it's a lot of code, of course, right? If you don't have the time and you prefer to just download the one from Peter Shirley and use it, the thing is, you need to study the book. In the end, you need to study and to check what is the code is doing, and that is also related with our lectures because this lectures that I'm having on these days, for example, today's lecture, everything is basically related on how this path tracer is implemented, right? So if you are watching the lectures, studying the lectures, understanding what I'm saying on the lecture, and also checking the code and the book, you'll be fine. Okay, and obviously for the second part, there's no code for the second part. Well, there is, but yeah, give me a second. The thing is, yeah, the second part you need to code it yourself, of course, but that is basically just adding to the first part, right? You add stuff, and yes, I know we know that some people, I mean, some of you don't have experience in C++. So remember, you could, if you want, you could implement everything in a different programming language. That is also allowed. Um, I mean, but it's up to you, right? I mean, it will be, I don't know, if maybe you maybe you choose a very obscure language that nobody knows, and that will make our life uh, not as easy, right? To help you, for example, or it will be. And someone did it in Haskell. Yeah. So if you try to implement a ray tracing in Haskell, maybe we will not be able to help you with that, right? So that is up to you, right? So if you think that you have enough experience in Python, that is perfectly fine. And also another thing that I want to make it clear is there are many ray tracing implementations outside. If you go and if you go to Google, for example, and you said like minimal ray tracing, you will see a lot of videos that actually with actually very good implementations. There's one video, for example, in which they implement a very minimal, of course, ray tracer in like 30 minutes, and it's probably like 50 lines of code or something like that. There's one guy also in YouTube that actually implements the entire first book, like literally the first part of your assignment. And there's the video in YouTube. I think it's divided in 3 videos or something like that. So he took like 2 hours or something, and he posted on YouTube. So yeah, basically if you Google or if you go to YouTube and search for ray tracing one weekend, you will find the video, right? Someone is already uploaded there. So yeah, in the end you can see uh, the way you actually can implement it, right? Yeah, so there are a lot of resources out there. If someone still have problems with the ray tracer, again, please ask on Piazza, send me an email. Yeah, so if some is like really struggling with this assignment, yeah, let us know, and we can obviously help you. And again, the labs will focus on that. I've already asked that to the TAs, and yeah, because obviously our purpose is to have our students to succeed, right? To have, yeah, yeah, you need to succeed on the course, right? And that is obviously our purpose. Okay, so that is regarding ray tracing assignment. Then we have the theory for assignment. So the theory for assignment is already there. There were a couple of people asking about the bonus points because, yeah, I think it could be probably confusing, that it seems probably too easy, right? Basically, it's the same exercise, right? So just different version of the same exercise. That is actually on purpose. If you go and check previous editions for this class, usually the last theory assignment is very small and is very easy, right? It's very straightforward, because in the end we want you to focus on the last part, right? Which is basically the ray tracing assignment, and then obviously to the final and everything, right? So usually it's easy. So also in this case, the bonus points are also easy. Someone is asking, is theory 4 due to December 1st? First page is different from PDF. Oh, I didn't know that. Let me check. Good question. Let me check. It should be, I think it should be December 1st. But let me check. Let me check. Let me check the web page. So the web page says December 1st, okay? And then I guess you can't see my screen, right? December 1st. Yeah, it's the same. December 1st and December 1st. Yeah, for theory 2. December 1st is Tuesday. Oh, so yeah, Tuesday. No. there is no typo, right? Well, I'm talking about theory 4. I'm not talking about ray tracing is of course for December 4. Right? Oh, sorry, it says Friday. Yes. Yes. Sorry. Yeah, that is obviously a mistake. I can fix it. Thank you so much. Sorry, I was not. Yeah, I thought you meant on the PDF. And can fix it right away. Yes. Okay. So I'm fixing it. Give me a second. I'm fixing it. Da-da-da-da-da. Da-da-da. That is my super long password. Okay. There you go. Okay, it's fixed. Yeah, we always need to fix bugs at the moment they appear, right? That is better, the best strategy. Okay, so that is, and I will show you actually an example of theory 4. So yes, if you were wondering what's up with this theory 4 bonus, is just the same exercise with different numbers. Yes, it is. It is. So my suggestion is, I mean, you can obviously solve it by hand with your calculator and with ruler and everything, but I would say that maybe it's better for you if you can code it, right? And you just, right, it will be obviously easier for you to you create your own code for that, maybe a script in Python or whatever. It will be obviously way easier for you to get the bonus points for that one. So those are very easy bonus points actually, and it will help you a lot. I mean, coding that, coding theory 4, it will help you a lot with the final assignment and also with the final exam, and also with the ray tracing assignment. Okay, and also last thing, last pending stuff is that the student evaluation of teaching survey is already there. So I received an email from the department, and I need to give you time actually today to solve it. So today's lecture, I hope, could be a little bit more compact. Why I'm already take a lot of time talking about this. But yeah, basically you need to do the student evaluation teaching survey. I got an email from the department saying that you should have received an email already. Have you? Do you have an email regarding the teaching survey? Yes. Okay. Yeah. If okay, it means that you have it already. So at the end of today, I will ask you if you can, because obviously this is voluntary, but it will be nice if you can do it. And I think it will be available from today or yesterday or something like that, since December 6th or something like that. Okay, so and this is an example of theory 4, right? So we have a ray that is basically hitting this part of this object, and if you're wondering why we have this weird normals and things like that, well, this is a kind of like a simulation of what could happen if you apply a normal map to an object, right? So we have an object like this. This is like a box, and of course, then the actual normal from this vertex should be kind of in this direction, right? That will be the actual normal for that object. However, these normals right here, right? These are fake normals that could be we could have read those from a texture, for example, right? So I'm giving you these directions, I'm giving you these normals. It means that when you compute the intersection between the ray and this segment right here, right, and this is the intersection, you need to also compute the interpolated normal, right, which is basically taking from their parents, right? So this is the interpolated normal between this normal and this normal, and that is obviously depending on the distance of the intersection. Once you have that, you can compute this angle, and if you have enough information regarding the index of refraction of the outside and the index of refraction of inside, maybe this is glass and outside is air, you can obviously compute the refraction angle using Snell's theory, right? And that's it. You get the ray, right? That is obviously bended, right? You get the new ray. Now you intersect with this segment right here, and this segment right here has another normal that also need to be interpolated from these two normals here, and you basically compute the same. Now the exit angle, and there was, I think there was one student that was asking me when I was explaining refraction, if the angle, if the last angle, when basically the rays is coming out from the sphere, because we had a sphere, remember, and the angle that was coming out of the sphere, it was basically the same as the incidence angle, right? The angle in which the ray was getting inside the sphere. And I said, yes, the angle, right? The angle, the entry angle, it is the same as the exit angle. In that specific case, of course, in the case of the sphere, right? Because in the case of the sphere, the normals are basically pointing to the same direction, but because, yeah, they're basically pointing on the opposite direction of the center of the sphere. But this is not the case, so please don't take that into account. Don't assume that this angle will be exactly the same as this, because it's not, right? You need to compute obviously the exit angle, and then this obviously the ray will continue until touching this thing, and obviously the color needs to be interpolated, right? So in the end, it's just it's an exercise of many things that we discussed already over the lectures, right? But that is theory 2. That is an example. Okay, so any questions about the pending stuff and also those things? Oh, and yes, someone is asking also TA survey. Yes, remember that you will evaluate me, right? I mean, as a teacher, and also the TAs, and that is obviously very, very important for us. So yeah, please do. Okay, so depth of field, we said that this is something that happens with the camera, depending on the aperture of the lens. So if the lens is letting a lot of light coming inside the sensor, right, we have something, we have a very shallow depth of field, and we could have an effect like this, right? The flower is very crisp, very focused in a very specific plane, but everything that is farther from the camera or farther from the focus plane is obviously blurred, and everything that is away, right, away from the focus plane, either closer to the camera or away from the camera, is basically getting blurred. And so the thing is, how can we achieve this on ray tracing, right? Because this type of effects are obviously known since almost the beginning of photography. Like depth of field is known from the beginning of photography, but computer graphics obviously is way more recent, right? Computer graphics started people were already talking about this in the 60s and things like that. So it was like, okay, are we going to simulate an actual, I mean, the refraction of an actual lens and things like that? I mean, you could obviously, right? You could create a 3D model of a lens and actually you could shoot rays through that, right? Fictitious 3D model, not fictitious, sorry, through a 3D model of all the objects of your glass, and basically compute all those refractions, right, that are coming inside the glass, and that will be possible, but it will be incredibly expensive, right? So the way we actually do it is just with a geometric trick somehow. So imagine that you have something like this. We have a camera, we have a ray that is coming from the camera from a very specific position in the space, and we have the image plane. And again, remember, the image plane is just a series, it's a set of pixels. For each pixel, we throw a ray that is basically, it has the direction from the origin of the camera to that pixel in particular, right? So imagine that we are sampling, right, or ray tracing this pixel right here. So we throw this ray, and we somehow want to simulate this depth of field and have some of these objects in focus and some of these objects blurred. So the way we do this is by create a fictitious element on our scene called a focus plane. It's not a 3D model, this is just a mathematical entity that you create in your code, and just basically determined by a focus distance. Basically, it's just a plane that is at some distance from the ray, sorry, at some distance from the camera, and that it obviously it is needs to be parallel to the image plane. Okay, so it's basically just a distance, right? You have your camera and you said, okay, at whatever distance I want to focus everything. So once you have your focus plane, you take your primary ray and you intersect your primary ray with this object right here, with this focus plane, and this will be the intersection, right? You agree? That intersection represents the focus point, right? So this obviously represents the focus plane, exactly the position in space in which everything will be crisp or focus, and yeah, and you get this intersection. So the next step is actually very easy. We just create random positions from the origin of the camera, and usually we do this by just creating random positions in a disk of a certain diameter with respect to the center of the camera. Of course, here I'm exaggerating the geometry here, right? I mean, this distance here is impressively big, right? It's almost as big as the image plane, right? Remember, this is the image plane. So in reality, it will not look like this. But imagine, right, that we do is just take different positions. It's like randomize the position of the camera. And basically what we do is, instead of shooting a single ray, which it was the original idea for ray tracing, right? We shoot a number of rays. We shoot several depth of field rays that are coming from those random positions, right? So the thing is, we take those random positions, we take the vector between the focus point and those positions, and that will give me, right, a direction, and I use that direction to basically create these rays. So what will happen is, obviously the objects are obviously closer than the focus plane, because you're taking all these rays and in the end just taking the average of those. Remember, we are sampling this pixel in particular, right? So instead of just sending a single ray and getting this color right here, for example, right? Now we're sending a lot of rays. We're sampling a lot of different places in the world, right? And you're taking basically the average, right? So some of those rays, for example, are going to touch this guy and the color will be purple. But some of those rays are probably touch this guy right here, right? So in the end, when you average everything, what you will see is that objects that are closer to the camera or getting away from the focus plane will get blurred, and objects that are getting away from the camera, away from the focus plane, are going to be also blurred again, right? Questions about depth of field. Okay, and someone is saying, why random and not an even distribution? Very good question. Actually, it is an even distribution. Yes, I mean, yeah, I said random, but yeah, that is imprecise. Yes, we usually compute it again as a disk of random, as a disk of points, and I mean they could be random. Actually, there are obviously different ways to implement it. The naive way to do it, for example, is maybe to create random positions in a tiny square of n by n, right? Depending on the size of sampling that you want to fake, and just test if they're basically inside the circle or not, and that will give you a disk of points inside. If you want to get a better quality of the sampling that you're doing, yeah, basically the best way is to have an even distribution of these points. Someone is asking, so as long as objects are further away from the focus plane, gets more blurry? Yes. Do objects closer from the image plane affect the focus of objects further away from it? Somehow, yes. The thing is, if, for example, imagine that this sphere is a bit higher. Imagine that it's a bit higher. It means that, again, remember that we were sampling this pixel right here, right? So originally that pixel was only seeing the purple sphere, right? So now, instead of having only the purple color, now it will have an average from the purple color, because a lot of rays are actually hitting the purple color, but also it will have a little bit of green, right? So somehow the object that is, it's closer to the camera, because it is blurred, is affecting the color of the one that is actually in focus. But yeah, they affect each other, of course. Okay, I might just have that closer to the image. Yes, so Tommy is saying, I imagine stuff that is closer to image plane just blocks the visibility of the stuff behind it. Of course, yeah, yeah. And because it is blurred, right, it will be kind of also, I mean, the blurriness of those objects will kind of be transparent to the objects right behind. So yeah, the objects behind, yeah, it doesn't matter if they're, despite the fact that they are basically in the focus plane, maybe you cannot see them clearly because you have something that is blocking, that is blurred, right? Okay, can that average of that color be a form of anti-aliasing? Well, that's the thing. This is very similar to anti-aliasing, of course. So the anti-aliasing, the only difference with anti-aliasing is that the rays are basically the directions, and the direction is different, right? Because with anti-aliasing, what we do is we get from this, sorry, my light went off. So we get from this point right here, or from the original point of the camera, right? We just shoot to different positions, but with the same origin of the camera. That is what we usually do in anti-aliasing, right? So it's exactly the same. The only difference, conceptually or geometrically speaking, it is exactly the same. You're just shooting different rays, a lot of rays in different positions or in different directions or from different positions, and you're just taking the average. So yeah, it is equivalent. Okay, someone has a question. Yes, David. Oh, give me a second,
yes,
David, because I cannot hear you. Give me a second. Yes.
Hello? Right. So for depth of field, does it have like a concept of like a focus field similar to the camera?
You could. It is. So the thing
It
is,
is?
it is because again, imagine in this image right here, I'm exaggerating the separation between these points. I mean, in reality, they're not as separated. This is just crazy. I mean, the separation I have here is almost as big as the image plane, right? So in real life, it is way smaller, and we will see if I drew this scene with the actual angles, right? It will always almost look as a straight line, almost as a straight line. So the thing is, yes, the objects are very close to the focus plane, are or either exactly in focus if they're exactly on the focus plane, or if they're just going away, they will start to get to get blurred. So there you could define a distance for the depth of field, right? So for this, the area in which your objects are focused or not, with a threshold, for example. So
Yeah,
that is
I was thinking like
that is usually
maybe
the way you do it. So yeah, so for example, what you usually need to do it is you if the objects are basically getting away from the focus plane, you will have a larger difference between the sample rays. You agree?
yeah.
So you could measure that difference, and you could define a certain threshold. So basically, if you want to have a measure of the distance in which things are in focus or not, you could use that threshold. So you will say, okay, my threshold will be, I will consider objects in focus if the difference between the sampled rays is not larger than, I don't know, 2%, right? You could actually use that and compute where is exactly that happen, and you could eventually get to the actual distance from which the difference is starting to get to be less than 2%, and then it will be basically no difference, and then it will come away from the camera. It will start to, right, the difference to be larger again until it's more than 2%, and that will be your next distance, right? So yeah, you could do it.
Yeah. I think like we can play with the distance between those random rays to like make the blurring more effective or like less effective.
Yes.
Is that possible?
Yes. Yeah.
Okay.
The way the thing is, usually in the render engines prior to, I think, maybe the year 2000 or something like that. Usually the way this yeah, every render engine was created, they usually got like the names of the technical implementation they were using. What I mean is, you could use different strategies to for your variables, right, to control this effect, right?
Yeah.
So
I see.
if I so for example V-Ray, that like 20 years ago, V-Ray, that is one of the most one of the most popular render engines, or Pixar RenderMan, for example. The way it was determining the depth of field, for example, it was just with a number, right? It was saying like, I don't remember exactly the thing, but it was like a gap or something like that, and they
I
were
see.
actually measuring the angle from these different rays, right? But that is not as
Mhm.
intuitive for someone that is maybe not expert in computer graphics, that is maybe an artist, and maybe an artist is more aware of photography concepts, right? So if you see the modern version of V-Ray or Arnold or RenderMan, or like modern render engines, they usually give you the same values that you can see in a camera. So you can see in Arnold Render, for example, or V-Ray, the modern versions, you can see f, you can see shutter speed, you can see ISO, you can see the actual uh, parameters that you can see in a real camera, despite the fact that inside, right, there is no ISO, there is no actually aperture, right, there is no diaphragm here. We are kind of faking a diaphragm just by putting points in a specific distance. But yeah, you can you can use whatever you want to define it.
You to simulate this. Okay, I see. Thank you.
Good. Okay, so let's continue. Now let's talk about soft shadows, which is also something interesting that we discussed already. So if I have a scene like this, I have a ray, this is my image plane, I have this floor, I am sampling a very specific pixel, this one right here, and this obviously the intersection. We know that if we want to compute the shadow, if this object is under shadow or not, we need to throw a secondary ray in direction of the light, right? We discussed this many times. So in this case, obviously this object is blocking this intersection, is blocking the light. Of course, means that this will be under shadow. The thing is, how do we compute okay, and obviously if you continue to sampling the floor, right? For every point on the floor, there will be some points that are visible from the point of view of the light, or invisible from the point of view of the light, or non-blocked or blocked or occluded by the light, right? So the actual volume, right, that is representing the volume that is representing the area that is blocked by the light is called occlusion volume, right? So everything that is basically on that occlusion volume, it means that it's under shadow with respect to this light in particular. Sorry, I think David, I think you're still not muted. Thanks. Okay, so that is occlusion volume, right? So the thing is, how can we achieve the area shadow effect? So remember, what happens in area shadows, area shadows are obviously coming from area lights, is that now because the light is not exactly a point, right? It is basically literally covering an area. So there are certain parts of the floor that are actually visible from certain areas, right? Certain points of the light, and there are other areas from the floor that are totally occluded, right? So we call that umbra, is the part that is always dark. It doesn't matter, right? I mean, depending on obviously of the size of the light, but the part of it that is always black is the umbra. It's also called shadow core in some computer graphics systems. They also called shadow core. And the penumbra is basically this area right here, right? The part that it gets softer because it's basically getting away from the umbra, and is getting this positions right here are getting a bit more chance to be illuminated by certain areas from the light. So basically, they're not in, yeah, they're less in shadow, right? Like in a gradient until basically you're lit by the entire light. So yeah, how can we compute this? So the way we do it is just throwing a lot, a lot of rays. So you get into this point right here, right? And instead of sending a single ray in direction of the camera, sorry, in direction of the light, we create a bunch of random positions. Or again, when I said random, you understand. I mean, the distribution could be even, right? But a evenly distributed positions or random positions, basically randomizing the position of the light. And obviously that will depend on something, right? I mean, if you're creating, if you're working with your variables, that variable could be, I don't know, a diameter for your area light, and maybe you're treating your area light as a disk, or if you're treating your area light as a rectangle, for example. Well, those positions, they need to be created kind of forming that rectangle, right? So basically you create, right, fictitious positions for your light, and instead of sending a single secondary shadow ray, you just throw more rays and you take the average, right? So in this case, for example, most of those rays will be blocked and only a few of those will be basically lit, right? It will get light. So it means that this object in particular, or this position in particular, will not be totally black. It has a certain probability of have a little bit of gray, right? Because there is just a tiny portion of the light that is actually covering that area. So of course, if we just keep, right, sampling the floor, you're shooting rays for the entire image, right? So we need to basically sample the floor. If you're getting one of the positions that are actually inside the umbra, it is clear that despite the fact that we are now shooting different rays, all those rays will be blocked, right? So for all the objects that are basically sampled inside the umbra, the their chance to get light is basically zero, right? So they will be obviously black. And the opposite happens if you have something that is almost in the other side of the penumbra, right? I mean, almost getting out of the penumbra. You're shooting different rays, and more rays are basically, right, getting covered by the light, and only some of those are actually occluded with this object. So this point right here will be less black. So in the end, you will see something like this, right? The umbra is totally black, and you will start to have like a gradient from black to white. I mean, we're not talking, they will not be, the color of the floor will not be literally white or literally black, right? We know that before using, when we were, if you compute ray tracing shadows, and you're, I don't imagine that you create a function for ray tracing shadows. What that function will tell you is it will get you a boolean, right? Either true or false. It's you're either occluded or not. So if you are occluded, we said that we usually do is we take the color, right? The color of the floor, and we drop the specular and diffuse values, right? The specular and diffuse components, and we only keep the ambient color, right? So in this case, if you now compute soft shadows, instead of having true or false, right, you will have a value, right? So I'm representing that value with black and white, so you can represent it, let's say, from 0 to 1, right? And you could use that as a weight for your specular and diffuse components, right? So if you are basically here, your value will be 0, it's black, right? So your value will be 0, and you basically multiply your diffuse and specular times 0, you basically only get the ambient component, right? And as you are basically coming away from the umbra or from the shadow core, this value is getting way, right? It's closer to 1. So let's say that at this point right here is 0.05, 0.5. Well, now you multiply 0.5 times your ambient sorry, times your diffuse component and your specular component, and your object will actually look pretty good, right? Okay, so let me see if you have questions. So, is there a name for this method of sending rays from different locations, or is it just sampling? I mean, yeah, usually called scatter rays or multi-sampling. Yeah, it's just like a generic name. Is there a reason why we can't implement a gradient effect instead of sampling? No, there is no reason. This is one way to do it. This is usually the way we do it. I don't understand what you mean by gradient effect. Maybe, for example, let's imagine that you compute the shadows with with the other technique that we saw, that is the shadow maps, right? So remember, shadow maps, they work differently. You have actually a depth map that you get from the position of your light, and you use that information to decide if things are basically inside or not. You could, for example, apply like a blur effect to that shadow map, and you could somehow blur the shadow, but that will be not as realistic on the places that are basically closer to the object, right? If you just blur the entire shadow, you will look very weird. This is a better approach in terms of geometry. The shadows computed as with this strategy, they will look almost exactly as they appear in real life. They look very good. Actually, I think, yeah, probably right now, every modern render engine based on path tracing or ray tracing, namely Cycles from Blender or V-Ray, Arnold, whatever, they are probably, everyone is using this. Okay. Any other question regarding soft shadows? Okay, I'm thinking the exam question will be just increase the size of the area. Maybe. Yeah, that could be a valid question for yeah, for the exam. Okay, so now let's talk about motion blur. So these images, these are not renders, these are obviously real. These show what motion blur is. So motion blur is what happens is that in a real camera you have something called shutter, that is a mechanical piece that basically blocks the light that is coming in your camera. And I want to turn my camera on. Give me a second. Give me a second because I want to show you something. Okay, so wow, it's very slow. I will stop sharing, and I will activate my camera. Can you see me? I had another light here to make it better, but I think I'm running out of battery for that one. Okay, so this is, can you see me? Yes, okay. So this is an old camera, a mechanical camera, right? So if we take the glass, this is an example of what I was telling you about the lenses, right? So this is the diaphragm. I don't know if you can see it. No, maybe not. I am opening or closing the diaphragm. Yeah, it's almost impossible to check it, but okay. So this is the camera, and if I put the camera, so you will see it has like a mirror inside, and that was basically the shutter speed. It's super fast. It opens the shutter, and it lifts the mirror, right? But basically, it will allow the light coming into the sensor. I mean, this was a film camera, so there's no digital sensor here, and of course the glass is here. So if yeah, my light is away, it doesn't have any battery anymore. Okay, so if instead I put the camera in something called bulb option, I will be able to click and basically open the shutter, and basically the light is coming into the sensor or the film, right? As long as I want, and then I release. So what I did is a very slow shutter speed. So the shutter speed is basically how fast the shutter opens and closes. So what is happening in this pictures right here, let me share my screen again. So what is happening in, can you see my screen again? Okay. Yeah, so people is saying overexposure. Yes, of course. I mean, if I do that like in real life, yeah, the image will look totally white. Obviously, I exaggerated because I was using bulb and I just lift the or open the shutter speed for a lot of seconds. But yeah, but the thing is, with longer exposure times or longer shutter speeds, what happens is that objects that are in movement with respect to the camera will appear blurred, right? But this is called motion blur because they're blurred in the direction of the way they're moving, right? So for example, this picture right here, the taxi is obviously fixed with respect to the camera because this person, like Ken, was getting the camera right, like very close to the window, and obviously the window is not moving with respect to him, but everything else is moving with respect to you, right? And you will see that, for example, these objects right here very far, these objects are less blurred than these lights right here, right? Because at this point, the speed of the car is way more, right? Again, with respect to the camera, than this object right here, or maybe this car. And it's clear that this car is going faster than this one with respect to the camera. So the same happens here. This is a picture that was taken in the night using a tripod. So it is a long exposure picture to get all the light, right? Because it's dark, obviously, and there's not much light. And the cars that are basically passing by, right, are leaving trails of lights, right? So motion blur happens again when you just decrease the shutter speed. So it is also a very cool effect that you can do in rendering, right? So imagine that we have something like this. We have a sphere that is basically falling, and the sphere in t0, let's say that t is time, right? It could be t or it could be frame. So in frame 0, the ball was right here and it's falling. So in t40 is here and the t60 is here. So if you're creating your renders, right, and you have that animation, and you take the sample of this ray in particular, right, you're sampling this image at time 40 without doing anything else, the sphere will look in focus, right? I mean, depending on if you're doing depth of field or not or whatever, but it will be basically in focus, and it will be still. So it's not very realistic, right? So the way we solve the problem of motion blur is by, again, shooting multiple rays, but now instead of shooting multiple rays in different positions in space, in this case, we shoot different rays or multiple rays in different positions in time. So we use time as a variable. So in this case, for example, we can sample from T38 to T43. So we are basically shooting 6 rays. I'm not drawing those rays because they're exactly in the same position. So the rays, they don't change. The origin and direction of those rays are basically the same. But now we're just sampling the world, right? Sampling everything 6 times, going back in time and going forward in time, and basically taking the average. We always do that, right? So for example, in this case, this is how this sphere will look if it's sampled with 6 motion blur rays. And with 10 motion blur rays, it will be way more blurred, right? Because of course, you're increasing the shutter speed, you're increasing the amount of frames that you're sampling, and you obviously need to increase the number of rays. So in ray tracing or path tracing, if you want to perform motion blur, this is what you do, right? You do exactly the same strategy of multi-sampling, but now using time instead of position. So at this point, you might be wondering, so every time there's a problem in ray tracing or path tracing, we just shoot a lot of rays? And the answer is yes, we do that. We just throw a lot of rays. And this is an example of what you could obtain, right? If, for example, here a lot of boxes are falling and rotating and everything, and this with one motion blur looks like this. And that's why ray tracing is so expensive, right? Because yes, the solutions in the end is just throwing rays, throwing more rays. So let's see a very quick example. Imagine that we will compute the amount of rays per pixel, right, in a specific image, right? A modern image in computer graphics could have millions of pixels, right? But let's talk about only a single picture. So imagine that we are doing path tracing, not ray tracing. So if it's path tracing, it means that we need to compute indirect light, and we are actually we are sending a lot of, for every time we hit something, we need to send a lot of rays, secondary rays, right, to cast the light that is basically getting from contribution for different objects, and we get this color bleeding and things like that. So let's imagine that is 10 rays for indirect lighting, and then you have 10 more rays to compute soft shadow, right? Because maybe you want your render to be very fancy and you have soft shadows. Well, you need to multiply 10 by 10, because for every ray from indirect lighting, you also need to compute your soft shadows. So you need to compute 10 rays for those. And then you want to also apply depth of field, and you basically, to apply the same strategy, to multi-sample with 10 rays, right, for every sample. Well, everything needs to be now multiplied by 10. And then you apply motion blur, maybe 10 samples for motion blur, multiplied by 10. And in the end, because you could have anti-aliasing, you are also applying 10 samples per pixel. Well, you multiply everything together and you get 100,000 rays per pixel. And that is why if you get the first part of your ray tracing assignment, you will get probably between half an hour and 35 minutes to compute the final image, right? Because it is incredibly expensive. Of course, I'm oversimplifying this, and the way we solve this is by using acceleration techniques. That is basically what we will talk about later. And yes, I think we can finish for today. I was hoping to give you a bit of time today for solving the survey, but but we need to finish. So please, if you have time, please go check that email and go and please solve the student evaluation teaching survey. That helped us a lot. Is there any final question? Somebody's asking, the first part may okay, someone is saying the first part made the image in a minute for me. Well, that is very good. So you finished the first part. If it's a minute, that is perfectly fine. Yeah, well, it will depend on your computer, right? If it's an old computer, it can be very slow, and also depending on how much rays are you casting, right? So for the person that is bragging that your computer is taking only 1 minute, I guess the number of rays you're shooting is not too much. So crank the number of rays, crank the number of anti-aliasing, crank the number of basically all the scattering parts from the code, and you will see that your image will look way better without noise, but it will take, it can take half an hour or more. Okay. Okay, good. So if you don't have any more questions, I think we can finish today. So thank you so much. Again, please go and sign up for the face-to-face. Please answer the teaching survey, and I will see you on Wednesday. Bye, everybody.
Hello, I have a raised hand.
Oh, yes, sorry, David. Yeah, you have a question.
Yeah, can you go field slide earlier? Like, go field slide back. To the ball falling image.
Yes,
Yeah. I was wondering, are you shooting? You're shooting from the camera to where? You're shooting rays to where?
We are shooting. Okay, remember that the rays we shoot is always from the camera to the image plane. The image plane has a certain number of pixels, right? So for every
Yeah.
pixel on your image plane, you compute a direction and then you shoot the ray. So imagine in this case in particular, I'm sampling a pixel that is basically in the middle of the image, right? So I'm using that
Yeah.
direction in particular. And this motion blur rays, let's pretend that you have 10 blur rays, you don't modify their origin or the direction. You only the only thing you modify is the time that you're sampling, right? So just basically take the image in, let's say that the original time was T40 or for the frame 40, right? It's almost
Mhm.
like render the entire image again for T minus 1, and do it at everything again for T minus 2, T minus whatever, right? So for T minus 1, minus 2, minus 3, minus 4, minus
Yeah.
5,
Yeah.
and then the same for T plus 1, plus 2, plus. You're literally computing everything 10 times and just getting the average. That will give you
I
this
see.
effect.
Okay. Okay. I
Yeah.
see. I see. Thank you.
Okay. Well, so see you. Thank you so much, and I see you on Wednesday. Bye.